Hello, I'm Sylvia Knight, Head of Education at the Royal Meteorological Society. In this series of short films, we're covering some of the background information that geography teachers may find useful if they're teaching weather and climate at secondary level. This is linked to the Weather and Climate Teaching Guide with accompanying classroom resources which you can find on our website, MetLink. In this film, I'll be looking at depressions. Mid-latitude depressions, extratropical storms, cyclones, if they're in mid-latitudes or low-pressure systems, they're all different names for the same thing. They all refer to the storms which bring the UK most of its weather, if it's raining or if it's windy, particularly in the autumn and winter. But what are they? Why do they form in the mid-latitudes where we are? Why do they cause rainfall and winds? These storms typically last several days, they're a few hundred kilometres in size, and they travel approximately eastwards across the North Atlantic. They're characterised by a swathe of clouds about the same scale as the UK, and when they look on a weather map, also known as a synoptic chart, they're distinguished by low pressure in the middle and distinctive fronts. They bring us both our normal and our extreme weather. The first scientific study and classification of these weather systems was performed by a group of Norwegian meteorologists, the Bergen School. The location was no coincidence. Bergen experiences a lot of these storms. Working in the early 20th century without the benefit of satellite and radar and all the things that we have now to tell us about how the atmosphere is behaving, this group did a remarkably good job of describing the nature of weather systems. So using only ground-based observations and weather balloons, they realised that depressions occur as a consequence of the pole to equator temperature gradient. As we live on a spherical planet, you can see in this figure, somewhere on the Earth's surface will always be at right angles to the sun's rays, such that the sun's light and heat is fairly concentrated. In contrast, in other areas on the Earth's surface that slope away from the sun's light, the sun's energy will be less concentrated. So as the Earth's surface is warmed by the sun, the more concentrated the light and heat, the warmer the surface. This is why the tropics are always warmer than the poles. The graph shows the latitude along the bottom, the x-axis, and the amount of energy on the left, the y-axis. The blue line shows that over the course of a year, the tropics receive more energy than the North Pole and the South Pole. That's not really surprising. The red line shows the amount of energy the Earth is losing to space. As you can see, the tropics also lose more energy than the polar regions, but the red and the blue lines are not the same. The graph shows that the tropics are absorbing more energy than they're losing, while the North and South Poles are losing more energy than they're absorbing. So if energy absorption and loss are the only factors at play, this would mean that the tropics would always be getting warmer and the polar regions would always be cooling down. But that's not the case, so something else must be transporting that spare heat and light and energy from the tropics to the poles. Storms, such as the mid-latitude depressions and tropical cyclones, are one of the ways that the Earth transports this heat from the tropics to the poles, maintaining the global climate as we know it. The rest of the heat is transported by the global atmospheric and oceanic circulations. The map below shows changes in the temperature from the polar regions to the tropics. The yellowy orange colours indicate warm air and the purpley bluey colours indicate cold air. As you can see, the rate at which the Earth's temperature falls as you go north isn't constant as you travel from the tropics to the polar regions. The colour bands are wide in the tropics and polar regions, and they're quite narrower in the mid-latitudes, so the temperature is falling off fastest as you go north in those areas. The Bergen meteorologists realised that this temperature gradient was a key part of the formation of weather systems. They saw the mid-latitudes as being where the warm tropical air met and fought the cold polar air. And as they were working at around the time of the First World War, when fronts were very much part of people's vocabulary, they referred to the temperature gradient as the polar front, so the boundary separating warm tropical air from cold polar air. Mid-latitude depressions form on the polar front because it's unstable. So consider a ball on a hilltop. Even if you nudge that ball very slightly, it will roll down the hill and end up a long way away from where it started. So that's an unstable situation. In exactly the same way, if something nudges the westerly winds blowing along the polar front from west to east, they end up a long way away from where they started. Imagine something nudging the westerlies, maybe a hill which the wind has to blow around. Because the polar front's unstable, the winds don't return to being westerly once past the hill. Instead, the nudge grows as a wave, and the wave gets progressively steeper. Then, in the same way that an ocean wave approaching the coast eventually gets so steep that it can't hold together any longer and the wave breaks, In exactly the same way, the atmospheric wave also breaks, stranding warmer air on the poleward side of the polar front and colder air on the equatorward side. And that's how depressions move heat from the tropics to the poles. However, we now need to consider why we get weather associated with depressions. Most weather processes ultimately rely on the fact that warm air rises. So where warm air meets cold air at the polar front or in a depression, it's always going to be the warmer air that rises. As it rises, the air cools, and so cloud and eventually precipitation will form. Remembering that air pressure is simply a measure of how much air there is above you, as the warm air rises, there's less atmosphere left above it, and so the pressure falls. The first law of thermodynamics tells us that as the air expands, it does work pushing the surrounding air out of the way, and this reduces its temperature. So the rising air cools, and as it cools, the rate of evaporation in that air becomes less than the rate of condensation, and you get cloud droplets forming. As that water vapour condenses into liquid water, latent heat is released, and that's the energy source for the developing storm. For example, there's enough heat released in a small cumulus cloud as that water vapour condenses into liquid water to power an average home for 17 years. As the storm continues to develop, some of the cloud droplets will become large enough to fall as rain, and that's why we get rain associated with these things. To look in detail at the weather associated with a depression, it's useful to break the depression into 4 distinct stages. The images below are map views, and the grey shading indicates cloud. Stage 1 shows the very start of a depression. There's warm air to the south of the polar front and cold air to the north. The winds are blowing from west to east. So to the left of the diagram, we have polar maritime air pushing into warm tropical maritime air ahead. This is called a cold front and is usually drawn in blue with triangle symbols on it, which you think are reminiscent of icicles. On the right side of the diagram, the warm air is pushing into cold air ahead. This is called a warm front. It's usually drawn in red with semicircle symbols. And again, those are reminiscent of the spherical sun. In stage 2, the wave has developed further. Taking a cross section through the stage 2 depression, the first thing to notice is that the fronts are not vertical, as it's always the warm air that rises. On the cold front, the cold wind blowing in from the west pushes into and underneath the warm air in front of it, forcing the warm air to rise. But on the warm front, the warmer air pushes into and over the colder air ahead of it, and we get the cloud and rain forming on the fronts. The front is drawn on the weather map where the front meets the ground. Looking at the warm front in more detail, you can see the progression of cloud type from cirrus, when the front is high in the troposphere, becoming cirrostratus, then altostratus, then nimbostratus, as the sheets of cloud associated with the tropical maritime air rising up over the colder air in front become lower and thicker. It's worth pointing out the very low gradient on the front. If the warm front is 5 kilometres high, then it may well cover 750 kilometres horizontally. They're not small features. And on the ground, the front itself may be anything between 1 and 20 kilometres wide. Wispy cirrus clouds are a really good indicator of an approaching depression. Closer to the ground, the cloud becomes featureless sheets, so stratus or nimbostratus when there's actually rain. When the front passes you on the ground, the temperature may rise by a few degrees. The cold front is much steeper than the warm front, as it marks the boundary between extremely cold dry air from high in the troposphere with the warmer tropical air. The weather on the cold front is therefore typically more extreme, with thunderclouds, cumulonimbus clouds, heavy precipitation and occasional hail, thunder, lightning and even tornadoes in the UK. Recent examples of tornadoes associated with cold fronts include the T6 tornado in Jersey and T5 tornado in Stalybridge, Greater Manchester in late 2023. By stage 3, the cold front has caught up with the warm front. Conceptually, it's easy to imagine that it's easier for the colder, more dense air behind the cold front to push the warmer, less dense air out of the way than it is for the warmer, less dense air behind the warm front to push the colder, more dense air out of the way. As the cold front catches up with the warm front, the two fronts mix to produce an occluded front, usually drawn in purple and with both semicircle and triangle symbols on it. Again, we can look at a cross-section through this stage of the depression. The cold front has caught up with the warm front and pushed the warm sector air off the ground. The warmer air in the warm sector is still rising, it's still there, it's just not there at the ground, so you can still get cloud and rainfall. By stage 4, the wave has broken and the system is dying away. The saying, red sky at night, shepherd's delight, red sky in the morning, shepherd's warning, is linked to the passing of a depression and our prevailing westerly wind direction. If the sun, setting in the west, shines its light on a depression in the east, giving a red sky, it's a sign that the depression has passed and better weather can be expected for a bit, because we probably won't get another storm for a couple of days. On the other hand, if the sun, rising in the east, shines its light on a depression in the west, then that depression has yet to hit the observer, so there's bad weather on its way. So you can think of the flip situation for the morning. So why are these low pressure systems? Consider the rising air in the centre of the depression on both those fronts. The rising air can't continue up into the very stable stratosphere above, so it spreads out sideways along the tropopause, the boundary between the troposphere and the stratosphere above. Air converges at the ground to replace the rising air, but that inflow is slowed down by friction. As a result, more air diverges at the top of the system than replaces it at the bottom, and the air pressure, the total amount of air above the ground, reduces. So that's why depressions and tropical cyclones, which are also in general produced by rising air, are low pressure systems. Winds blow around depressions in an anti-clockwise direction following the pressure contours in the northern hemisphere because of the Coriolis effect. In the southern hemisphere, the winds blow in a clockwise direction. So where does the jet stream fit in? The polar front jet stream is a belt of westerly winds in the upper troposphere with wind speeds up to 200 miles an hour. It sits at around 10 kilometres, the height at which aeroplanes fly. Transatlantic pilots make use of the jet stream to minimise flight times. We've explored why there are westerlies in the jet stream above the polar front in the pressure and wind film. So the jet stream is found where the poleward surface temperature gradient is strongest, so above the polar front, the same location where depressions form and intensify. The closer the temperature contours on the polar front, the faster the jet stream and the more rapidly depressions grow. It's also worth pointing out that depressions form in both the jet entrance, where the jet is accelerating, and the jet exit, where it's slowing down. Depressions develop to the right of the jet entrance and the left of the jet exit. As depressions on average follow the same path as the jet stream, it can be used to predict the path taken by an individual storm, and over a season the clustering of the tracks followed by depressions produces a storm track at the surface. The developing depressions interact with the jet and with the polar front, creating continental scale waves along its path. In the summer, the global circulation shifts north, and the polar front, the jet stream, and therefore the depressions tend to be further north in our northern hemisphere summer than in the winter. Usually the north of Scotland still experiences depressions in the summer, whereas the south of England doesn't. In addition, the equator to pole temperature gradient is less extreme in the summer because the temperature in the tropics are relatively constant through the year, but the poles are far warmer in the summer. Therefore, the temperature gradient across the polar front is smaller, the westerlies are weaker, and the storms tend to be less damaging. Since 2015, the Met Office, together with the Irish and Dutch Met agencies, give storms which are expected to cause disruption or damage a name. And then in addition, the Met Office also issues weather warnings to specific areas, which are colour-coded yellow, amber or red, depending on how damaging the wind, rain or snow is likely to be. The Environment Agency works with the Met Office to then issue warnings to places which may be affected by flooding as a result of the storm. In the southern hemisphere, we know that as the climate warms, the polar front and therefore the storm track and the jet stream will shift to higher latitudes. There's a lot less confidence in projections about what will happen in the northern hemisphere. In addition, we expect depressions to have faster winds and greater amounts of precipitation associated with them, associated with a warmer and therefore more energetic atmosphere. There are many useful sources of data for mid-latitude depressions, some of which we've given in the text below. In the next film, we'll look at microclimates.